Hi, I am Dr. G. Srinivasu, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this video, I would like to present the type 4 method to solve a differential equation of second and higher order with constant coefficients. Already in the previous videos, we have seen the general method and the type 1, type 2, type 3 models, which are shortcut methods to find the particular integral instead of using the conventional procedure. And here I am going to solve the problems using type 4 of the particular integral. So the type 4 is, if the given equation is in the form f of d of y is equal to q of x, where q of x is equal to e power ax v of x format. So v of x is any function of x, where v of x is any function of x. So it may be sin x or cos x, whatever it is, or x power k or tan x, secant x, whatever it is. If the given differential equation is of the form f of d into y is equal to q of x, where q of x is in the form e power ax into v of x. So how to proceed in shorter way to find the particular integral? So just I will give the working rule, just a two-step working rule. The yp is equal to 1 by f of d of e power ax v of x. So first, in the first step, you have to replace d by d plus a in f of d. Then you will get yp is equal to e power ax 1 by d plus a of v of x. Just replace d by d plus a in f of d. Then e power ax into 1 by f of d plus a of v of x. So just I am using shorter method. So I am giving the procedure only. I am not going in detail of the method. After this completion of this, we operate 1 by f of d plus a on v of x. 1 by f of d plus a. This means it is a function of d. And 1 by function of d operate on v of x. That we can use the general method or shortcut methods based on the function v of x. So very simple method. Just replace d by d plus a. So write e power ax first into 1 by f of d plus a of v of x. Now operate v of x on 1 by f of d plus a operate on v of x. That is the model. This is comes under type 4 of finding the particular integral of the equation f of d of y is equal to q of x. So now I will go with one example. Solve the differential equation d square minus 4 of y is equal to e power ax cos 3x. So clearly it is in the form f of d of y is equal to e power ax into v of x. Am I right? This is in the form e power ax into v of x. What is here? V of x is equal to cos 3x. So in this model, we apply type 4 method to find the particular integral. So first find the complementary function. So for this equation, we have both complementary function and particular integral. The solution, on adding, you will get the general solution of this equation. So before finding the particular integral, we calculate the complementary function. So as usual, write f of d here. F of d is d square minus 4. The auxiliary equation is f of m is equal to 0. F of m means replace d by m, then m square minus 4, 0. So I'm writing in factor form, a square minus b square is equal to 0 means a minus b into a plus b 0. That is m values are 2 comma minus 2. So the roots are, the nature of the roots are real and distinct. The roots are real and distinct. So the complementary function will be in the form c1 e power 2x plus c2 e power minus 2x. So this is the first part of the solution. Now we find the particular integral by using the method said above. So here yp is equal to the particular integral. Yp is equal to 1 by f of d of e power x cos 3x. So what is f of d here? What is f of d here? D square minus 4. Right? Am I right? 1 by I will write here. Problem is just changed. Yp is equal to, I will solve Yp. So how to find Yp? So now Yp is equal to, just I will do this on this. How to find Yp? So Yp is equal to 1 by, just wait, Yp is equal to 1 by d square minus 4 of e power x cos 3x. Am I right? E power x cos 3x. So it is e power x into v of x model. So the formula 1 by f of d of e power ax v of x is equal to e power ax into 1 by f of d plus a of v of x. So now replace d by d plus a. So on replacing e power x, right, first term as d e power x, and replace d by d plus 1. So d plus 1 whole square minus 4 of cos 3x. So this is equal to e power x into 1 by, so what is the denominator x? D square, and here plus 2d. So that is, on expanding you will get a d square plus 2d plus 1 minus 4. This is minus 3 of cos 3x. Am I right or not? So now this is equal to e power x into, so this is 1 by f of d of cos bx model. 1 by f of d of cos bx. So what you have to do? Replace d square by minus b square, minus 9. Replace d square by minus 9. Then what you will get? D square by minus 9 plus 2d minus 3 of cos 3x. So you are following the second type of finding of particular integral in shorter method. So just replace d square by minus b square. So on substituting this, you will get e power x into 1 by 2d minus 12, 9 minus 3, minus 9 minus 3 minus 12 of cos 3x. Now what to do? We have to make the denominator as a function of d square. So that can be done by e power x of 2d plus 12 by 2d minus 12 into 2d plus 12 of cos 3x. Of cos 3x. So how you write? Yp is equal to, now Yp is equal to 1 e power x. What already we operated with e power x, then 1 e power x d plus, we replaced d by d plus 1, then e power x into 1 by 2d minus 12 of cos 3x. Now we make it as a function of d square. So for that purpose, I multiply and divide with 2d plus 12 and 2d plus 12. I multiply and divide with 2d plus 12 and 2d plus 12 of cos 3x. Then what we will get? E power x of 2d plus 12 by, so in the denominator it is a plus b into a minus b form. So 4d square minus 144 of cos 3x. Now this is e power x into 2d plus 12 by, again it is a function of d square. Now what you have to do is replace d square by minus 9. Again it is minus b square, you have to replace. So 4 into minus 9 minus 144 of cos 3x. So I'm replacing d square by minus d square, minus 9. Then what you will get here? E power x, that is equal to e power x into 2d plus 12 by, in the denominator it is 9 fours are 36 and 144. This is 0818. So minus 180 constant will get of cos 3x. Now 1 by 180, 1 into e power x into, now operate 2d plus 2 with cos x, 2d plus 12 with cos x, that is 2 into d of cos 3x is one term. And what is the second term here? 12 of here 12 of cos 3x. 12 of cos 3x, that is equal to minus e power x by 180 of d of cos 3x. What will be d of cos 3x? D of cos 3x means d means d by dx. So d by dx of cos 3x, that is minus 3 of sin 3x. 2 already there. D of cos 3x is minus 3 sin 3x plus 12 cos 3x remains same. Then what is the value? Minus e power x by 180 and minus 6 sin 3x plus 12 cos 3x will be the, or on multiplying with minus sign, you'll get e power x by 180 of, on multiplying minus sin 3x into minus 6 plus will get, and minus 12 cos 3x, and this entire term is yp. So here I will explain again. Already we have operated with e power x, e power ax on replacing d by d plus 2. Then we replaced d square by minus b square as per the type 2 model. Still it is 1 by 2d minus 12 of cos a cos 3x. Now to apply the second model, it is a function of, it should be a function of d square. So to make it as a function of d square, I multiply and divide with 2d plus 12, and on operating we will get, this is the yp. Therefore, what is y? Therefore, what is y? Y is equal to yc plus yp is the required general solution of the given equation. Now we see another problem in the same model. Solve the differential equation d square minus 6d plus 9 of y is equal to e power 2x into x cube. So here also the equation is in the form f of d of y is equal to e power ax into v of x. So as usual, first write the complementary function, then find the particular integral. Here f of d is d square minus 6d plus 9, and then the auxiliary equation is m square minus 6m plus 9 is equal to 0, or we can write it as m minus 3 whole square. So m values are 3, 3. So the roots are real and equal. Therefore, the complementary function is yc is equal to, or cf is equal to c1 plus c2x into e power 3x. So because the roots are real and equal. Now, on coming to the particular integral, I write yp is equal to 1 by f of d of e power ax into v of x model and e power 2x into x cube. So in the first step, we have to replace d by d plus 2, and you have to write e power 2x as a front term, e power 2x into 1 by, you write in place of d plus 2, that is d plus 2 whole square minus 6 into d plus 2 plus 9 of x cube. So on expanding the denominator, it is d square plus 4d plus 4 minus 6d minus 12, and what is the last term? Plus 9. So on simplifying, what you will get? D square minus 2d plus 4d minus 6d, that is equal to minus 2d, 4 plus 9, 13 minus 12. 13 minus 12 is plus 1. So thus that will be the constant term. So I simplified this as, and write 1 by d square minus 2d plus 1 of x cube. Now we have to apply 1 by d square minus 2d plus 1 on x cube. We have to operate with 1 by d square minus 2d plus 1 to x cube. So I am writing the denominator as d minus 1 whole square form. This is d minus 1 whole square, d square plus 1 minus 2d. So denominator can be written as d minus 1 whole square of x cube, same. So the numerator 1 minus d minus 1 whole square and 1 minus d whole square both are same. A minus b whole square or b minus a whole square both are same. So I can write 1 minus d whole square also, and on writing in the numerator, this is 1 minus d whole power minus 2 of x cube. So this is e power 2x into 1 minus d whole power minus 2 of x cube. So as per the third type, we have to write the denominator as 1 plus phi of d notation. So it is reached to 1 plus phi of d notation whole power minus 2. Now it is in the form of 1 minus x whole power minus 2. So by using the binomial expansion, the expansion is 1 plus 2x plus 3x square plus 4x cube plus so on. So it is 1 plus 2d plus 3d square plus 4d cube plus so on of x cube. Now operate each term with x cube, that is 1 of x cube plus 2 into d of x cube. D means d by dx plus 3d square of x cube plus 4d cube of x cube, and higher degree terms will become 0. Now what you will get? E power 2x x cube. The same step here I am writing. 2d of x cube plus 3d square of x cube plus 4d cube of x cube plus so on. The higher degree terms will become 0. Now e power 2x, the above expression can be written as e power 2x. First term x cube as it is. D of x cube. D of x cube means d by d of x cube, that is equal to 3x square. So I replaced d of x cube is 3x square and d square of x cube. Once again we have to, d square means d square by dx square of x cube. So on differentiating one time it is 3x square and again you will get 6x. So that you will get here plus 4 into 6x differentiation, that is 6. So that is e power 2x into x cube plus 6x square plus 18x plus 24. What this is? The particular integral yp. Therefore, the general solution or complete solution y is equal to complementary function plus particular integral. So that is c1 plus c2x into e power 3x. Because the roots are 3, 3 repeated root, the complementary function will be like this. And the particular integral is, already we have solved that yp as e power 2x into this term. So that as it is copied down. So this is the solution of the given problem using the shorter method of the finding particular integral. So in this way, you can find the particular integrals when the function is in the form of e power ax into v of x. Now, I will solve another problem. Just the last problem of this session. So here there are different terms, e power minus x, x cube, e power x sin x. So what is the here equation? The operator form I can write d square plus 1 of y is equal to e power minus x plus x cube plus, what is the third term? e power x of sin x. So now as usual find complementary function and then particular integral. So what is f of d here? D square plus 1, and the auxiliary equation is f of m is equal to 0, or m square plus 1 is equal to 0, or m square is equal to I square, or m is equal to plus or minus I. Therefore, what is the complementary function? yc is equal to c1 cos x plus c2 sin x. So it is in the form of alpha plus or minus I beta, alpha 0 and I into beta also 1. So e power alpha x into c1 cos beta x plus c2 sin beta x. So this is the complementary function or yc of the given function. Now find the particular integral. What is yp? 1 by d square plus 1 of, here there are 3 terms, e power minus x, x cube plus e power x sin x. So find separately. You can find separately each term operation with 1 by d square plus 1 and add all these 3. So call this is equation number 1 and this is equation number 2. Now I am finding first 1 by d square plus 1 of e power minus ax. So this is yp, this is yp1, yp2, yp3. So on adding all the three, you'll get yp. So replace, according to the shorter method of type 1, just replace d by minus 1. Then it is, if it is not equal to 0, that means what is the value? E power minus x by minus 1 whole square plus 1. So what is the value? E power minus x by 2. That is the first yp1, first particular integral. Just replace d by minus 1. So minus 1 whole square, this is plus 1, 1 plus 1, 2. E power minus x by 2 is the first part. Now 1 by d square plus 1 of the second term, x cube. So this I can write it as 1 plus d square whole power minus 1 of x cube. So already the denominator is in the form 1 plus d square, 1 plus phi of d notation, 1 plus phi of d whole power minus 1 of x cube. So the expansion 1 minus d square, 1 plus x whole power minus 1 expansion, minus plus d square whole square, 1 minus x plus x square minus x cube plus so on. That is the expansion. 1 plus x whole power minus 1. 1 minus x plus x square minus x cube plus so on. So in expanding, 1 minus x means d square plus x square means d power 4, and higher degree terms are not required of x cube. Higher degree terms when operate with x cube, those terms will get 0. Now 1 of x cube, that is x cube, 1 of x cube, d square of x cube. That means 2 times differentiation of x cube. For one time it is 3x square, and again on differentiating it is 6x. D square of x cube derivative 3x square, and again differentiating you'll get 6x plus d power 4 of x cube, 4 times differentiation 0, that is x cube minus 6x. This is yp2, the second part of the particular integral. Similarly, you find the particular integral for the third part, that is 1 by d square plus 1. So how to find the third value? 1 by d square plus 1 of e power x of sin x. So this is we have seen already in the fourth model, e power ax into b of x model we have to apply. That means what we have to do, e power x, right, first term, and replace d by d plus 1 in the denominator whole square plus 1 of sin x. Then what we will get, e power x into 1 by d square plus 2d plus 1 plus 1 plus 2 of sin x. Am I right? Now we have to apply the model number 2, 1 by f of d of v of x. So replace d square by minus 1 square, that is minus 1 plus 2d plus 2 of sin x. Replace sin bx or cos bx. Then we go to approach second model. So e power x into 1 by 2d plus 1 of sin x. Am I right? Now, so what is the first integral? I will write here yp1 is equal to e power minus x by 2, and yp2 already we have calculated, that is x cube minus 6x. So here I am erasing, that's why I have written here. So this is equal to e power x into, clearly it is not a function of d square. So to make it as a function of d square, I multiply and divide with 1 minus 2d. In the denominator, you will get 1 minus 4d square of sin x. Then what you will get, x e power x by 1 minus 2d by, replace d square by minus 1 square again. So apply the same approach, 1 minus 4 into minus 1 of sin x. So then e power x by, so this is equal to e power x by 1 plus 4, that is 5. 1 plus 4 in the denominator. And operating with 1 minus 2d, 1 of sin x, that is sin x, minus 2 into d by dx of sin x, that is 2 cos x. So this is the particular integral of the third case, that is equal to yp3, third part. Therefore, the complete particular integral, the pi is equal to, from equation number 2, what you will get, yp is equal to, first one e power minus x by 2, second term x cube minus 6x, third term e power x by 5 of sin x minus 2 cos x. So this is the particular integral yp. So therefore, the general solution will be y is equal to yc plus yp, which is the required general solution of the given problem. So here we have applied the type 1 model and type 3 also, and here type 4 and type 2 also. So the problem covered all the 4 models to find the particular integrals in special cases. With this, I conclude my session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.